Good morning, everyone. It's a sunny day. Tuesday class asked me about this question here from last week tutorial 1.6.2. I think there's a mistake here where you need to observe that here we have Q or not P and P and Q or Q, so that we can factorize the Q out using the distributivity law. And then you will get statement disjunction with a false statement, which is the contradiction here. And then you can use the identity law to get the Q back, which is what we want. I'll update the docs later. I think another frequent asked question is about this. So if you have a P, then you can deduce P or Q. If you have P, then you can deduce P or Q. Any question you want to ask from last week lecture or tutorials? Anything you confused? Here encourage you to ask questions in the classroom. Okay. Let's recall what we did last time. So we said that two sets are equal if one is the subset of the others. So to show that two sets are equal, you need to show that A and B are equal, you need to show that A is the subset of B and B is the subset of A. And the proper subset is a stronger notion than a subset, where you need to check an extra condition here, meaning that A cannot be equal to B, which means there exists something in B which is not in A. Okay. This is the extra thing you need to check. Then last week we also talked about how these set could sit inside each other. Okay. And then we also talk about this, the proper subset. Set of proper subset. An empty set is an empty set. Okay. Yeah, today we'll explore more the properties of set. So first thing, we want to know how big is the set is. Yeah. So we have this cardinality. So let's given a set. Given a set, the cardinality of the set is the number element in X. Okay. We denote by modulus X. Okay. So if X has n element, then the cardinality of X is n. Okay. Where n is positive integers. Okay. Otherwise, S is co-infinite. Okay. So, for example, remember the clock number. So it's the 1, 2, 3, 2. So what's the cardinality of this set? Huh? 12. Okay. How about the cardinality of the empty set? 0. That means this one, I think I need to put non-negative. Okay. Yeah. Okay. So the code number and 5 are finite. Okay. So infinite set are what? So for example, the n z, the rational, the real, the complex are infinite. Yeah. Yeah. So okay. Next. Okay. So now, given a set, we can study all the subset inside the set. Okay. So the power set. This is called power set. The power set of X is another set. The set. What is the element? Set of all subset. Okay. And we denote by EX. Okay, for example, so let's look at this set here. 0, 1, 2. So let S be 0, 1, 2. So we proved that last week every set contains empty set and the whole set is a subset. So we must have at least 2 elements here. How about the set containing 0? So the set of containing 0 is a subset of X. Right? So you need to check by definition, check every element here is an element on the right hand side. And what else? What other subset do you have? Set containing 1, 2, anything else? 0, 1, 0, 2, 1, 2. Okay, good. Okay, so this is the power set of that. Okay. So now we want to introduce some operation between 2 sets. Okay. First, we will introduce the product of 2 sets. But before that, we need to introduce a notation, which is the ordered n tuple. So the order n tuple is the ordered collection. So the order is very important. If you switch the order, they might represent a different element. So A1 up to AN. So this isn't strange to you because it's like the SY coordinate. Right. So when n equals to 2, it is the ordered pair, which is like the SY coordinate. Okay. So we'll define the product of two sets using this. And the product we are looking at is called the Cartesian product. So let A and B be sets. So the Cartesian product of A and B we denote as A cross B. Is the set another set? Set of what? Set of what element? Set of all ordered pairs. Maybe. Where the first coordinate is in the first set and then the second coordinate is in the second set. Okay. So we will write A cross B as a set of ordered pairs A and B and B. Okay. Don't note that I put a dot column equal sign here, meaning I'm defining the set here. Okay? This is the first time this set appearing. So we look at, if you see this, the definition of it is this. Okay. So, for example, let's take A equals to 1, 2, and B equals to 2, 3. Okay. So what is A cross B? What do you have? Yeah, order pairs. So first one is coming from the first set, and then the other one is coming from the second set. 1, 3, 2, 2, and 2, 3. Okay, okay, good. And yeah, okay. So let me read up. So the next example is R2, yeah, which is R2, which you draw as a plan. Okay. So in general, A cross B is not equal to B cross A. So this operation is not commutative. So you can check on this example here. So find B cross A. You will see that they have a different element, so they are not equal. Okay, and also, actually, you can generalize this. Generalize this definition to n tuples. Cartesian product of n set. Okay. Right. So can be defined as the ordered end output. Such that A I is in here. So I going from N to N. Okay. So you can generalize this to N tuples. Okay. So last time we didn't make this precise, but today we will write spell it out specifically. So I think this one in the book is called the step builder notation. So set builder notation, we use a predicate and a domain. And a domain, and we define the truth set of P to be the set of elements X in a D. Okay, for which X is true. So the notation is so the truth set notation is X in a D dx. Okay, introducing this definition is because I want to stress the importance of writing the domain here. Okay, every time you need to specify the domain here because the set will change with the domain. Let's look at this example here. So let's say I study the same predicate in different domain, which is s to the power 4 is equal to 1. Okay, so we study it in the set of natural number, integer, real numbers, and the complex number. Okay, so the predicate haven't changed, but the domain I changed. Okay, let's see what's the set representing here. So what are the numbers in the natural number that satisfy S4 equals to 1? 1? Anything else? No? Okay. How about in Z? Huh? 1? Anything else? Minus 1? Anything else? No? How about in real? Huh? 1 minus 1? Okay. How about in complex? Huh? What do you have? I? Okay. What else? Huh? Square root 1? Square root 1? Square root 1 is 1, right? 1. Anything else? Minus 1? Minus what? Huh? Minus I. Okay. Yeah. So if you change the domain, your set might be different. Okay. So it's very important you state your domain. Where's your domain line? You can see that 1 is not equal to 2, 2 is equal to 3. Okay, maybe don't use this, use the ABC. So let's call it A. Okay, so A is not equal to B, B, C. Okay. So, and these are called the, actually this part is called the roots of unity. Fourth root of unity. So degree 4 polynomials has 4 roots. Okay, next. Okay, next. So given a 2 set, we can define another 2 set. We can define the union of sets. Okay. The union A, B, A and B. So we write as A cup B and A cup B. So what's the union? Is another set. So containing elements that are either in A or in B or in both. Okay. So in the set wise notation is A union B such that X is in A or X in B. Okay. So for example, what's the union of 1, 3, 5 and 1, 2, 3? Hmm? 1, 2, 3, 5. Okay. How about this? If you take the union of the reals and the n, what do you get? Ah, ah. Okay, good. So, whenever you see the equality of set, right? Okay, I want you to think of the set inclusion. Okay, go back to the definition. So, in this topic, one of the skill you need to master is to show the set inclusion. So, to show that two sets are equal, you need to show that one set is the subset of the other. Okay, and okay. So for example, let's show the first one. So to show the first one, we need to show that we need to show that for every x in the left hand side, x is in okay. So to show this, you need to take x in R union n. Okay. So by definition, x is either in R or in N, right? So X, then X is in R or in N. Okay. If X is in R, then it is in R. Right. If X is in N, is it in R? Ah, then X is also in R. Why? Because N is a subset of R. Okay. So in either case, X is in R. So you prove that hence S is in R, either way. Yeah, so this is how you show the set inclusion. Okay. The other way, you can try on your own exercise. Okay, next. Okay, This one will be interesting. So try to check this here. What time is it? Okay, 9:36. So let's look at the finite union of these closed interval here from minus I to I, which run from 1 to n. And also look at the infinite union of this kind of interval. Try spend 2 minutes to think about it. You can discuss with your friend what are these finite union and infinite union. Oh wait, before that, let me introduce this notation first. So you can generalize this gen this definition to finite union and infinite union. So what's this right hand side here is exactly what is on the left hand side. Okay. So this I is not important. You also can change to J. It's just a indexing number here. But what is important is this J run from this J and I are indexing in Z. Okay, there should be an order so that you know what's the next number. Yeah, try think about this finite union of intervals, closed intervals, and infinite union of closed intervals. So what's the definition of interval again? So the closed interval means all the real number that's in between the endpoint. If it is closed, then we will include that. Okay. So maybe it's easier to see that what's the relation between these intervals. So these intervals are actually subset. There's a subset relation between them. You see it? So if you imagine the line we have, the real line, okay, so we got 0 to 1, yeah, and then minus 1 to minus 2 to 2, and then minus 3 to 3, and so on, and keep going. So you can show that the finite union of this interval is actually what? Actually what? Huh? Negative n to n. Okay. So how to see it from the set inclusion? So you just this direction just says that everything in here is in here. Okay. So and then everything before is already in here. So that's means it's in here. How about the other side? The other side just says that the whole thing here is already in here. Okay. But infinite one maybe a bit tricky. Any idea for the infinite one? Any idea on the infinite one? So you keep expanding. Hmm? Ah, minus negative infinity. Uh, you mean something like this? Uh, we have negative infinity, but negative infinity is not in the real. It's not a real number, so we cannot draw something like this because there's no real. There's no yeah. This is not a number. So this two are not number. And then yeah. Huh? But n n uh no, it's not n because 0.5 is in here, but 0.5 is not in here. Not n. It contains n. So n is in here. So n is a subset of this infinite set. R, yeah, is R. So every number here you take, you can find, you can show that it is actually lies in some interval. Good. Maybe minus 7. Then every number here, of course, is a number here because I pick from the real. Okay. Yeah. Good. Next. So next, let us introduce the intersection. Let A and B be a set again. So the intersection set A and B. So we write as A cap. A cap, yeah. Now cap. A cap B is the set, another set. Okay. So how do we pick the elements? So the elements are in both A and B. Okay. A cap B is defined as the element such that it is in A and it is in B. Yeah. Of course, you can do the generalization to uh, finite union. Sorry, finite intersection. Intersection. Finite intersection. or infinite intersection? Okay. Okay, let's look at example again. So let's take the same set and intersect it. So what do you get? 1, 3. Okay, 1, 3. How about R intersect with N? Is N? Huh? N. Okay. Okay, good. So similarly, you need to, in your mind, think why is it the inclusion is true, okay? Every time you need to check the equality. Okay, next, I have a similar intersection question on the interval. So let's look at this intersection here. Okay, let's see what's the intersection of the closed interval from minus 1 over I to 1 over I. And then the infinite intersection of this closed interval. Give you another 2 minutes to try. Okay, anyone have any try on the first one? What's the finite union equal to? Hmm? Yeah, okay. Close or open? Close interval or open interval? Hmm? Huh? Close interval or open interval? Close. Okay, yeah. So you see that mm, you see that so if this is the direction, so you see that this interval here is lies in every interval here. Okay. And then how about this direction here? Okay. So to lie in every interval, the x must lie in this interval, which is equal to this interval. Okay. How about the infinite intersection? What do you get? 0. 0. Okay. Yeah. Set contain 0. Yeah. So I think this direction really is easier. So 0 is inside, is in between every how to say every so for every n you can find that 1 over negative 1 over n is less than 0 and 0 is less than 1 over n. Okay? This is how you can show it this way. And then the other way, The other way is maybe a bit harder. Okay. Infinite is a bit tricky. Okay, next. Okay. Yeah, so you can observe that so you can observe that the interval behave better with the union instead of intersection in the reals. So if you take infinite reals, then become a point, not an interval anymore. This is some properties of the real numbers. Okay, next. Next. What time is it? 9:41. Is it going too fast? Or okay. Next, that definition again. Okay, let's introduce this universal set. So the universal set is a set that contains all the objects under consideration. So we can create a universal set that includes all the set that we are consider currently. So for example, why we need this? So suppose U is the universal set. Okay. I should say there's another set. There's a subset of U. Okay. So the complement of the set A denoted by A bar is the complement A respect to U. Okay. Maybe you can ask why we are interested with the complement of the set A. Because sometimes set A is very hard to understand. Instead of understanding set A, we can understand the complement of set A. So understand uh, the what the space outside set A. So for example, the research I'm working on is something called the knot. So that's like the knot. Okay. So how to uh, differentiate whether two knots are the same or not? I don't know whether these two knots are the same or not, but I can study the complement of the knot. Okay. Study the space outside them. So you provide a new way to study this object. Okay. Yeah. So you also can think of this complement as a universe, right? Because in physics they come up with a theory called the string theory. So these loops or these knots will become the gravity, will represent the gravity. This is a proposed theory, but not proven yet. Okay, because I see too many times, so I tell some story. Okay. What else? Okay, so I haven't tell you the notation. So sometimes we will write, sometimes we write AC or U/N, okay, or U away. Yeah. Okay. So in the set builder notation, we will write x in yield such that x is not in A. Okay. For example, we have u equals to r. Okay. And then let's look at this set here. So the open interval from negative infinity to negative 1, union 1 to infinity. Okay. Then what is u slash A? Minus 1 to 1, close interval or open interval? Close. Yep. Okay, I think very good. So let's stop here and then let you see a diagram. So let's take a break and then we will look at this diagram later. 9:56, we'll resume. Go back to the slide. Oh, you got question? Yeah. Which one? Yeah. Oh, you take a look. Okay, okay, okay. Yeah, yeah. Complement also makes sense in the society. Like if you want to understand that person, but the person is very hard to understand. So you understand the people around him or her. Complement. Mm-hmm.
The English means it cannot. It cannot.
No, it's a set of zero, not zero. Set of zero.
Set of zero. 没事，这个不是重点，大家分析一下。
Okay.
If it's closed, we think we cannot get zero. But it is when it's open. When it's open, so we can get this.
Why?
The closed interval.
Yeah.
I think the result must include such a number. It can't be zero only.
Can you prove it?
It must have something like this.
Then you tell me what number is that.
I can't tell, but it's very close to zero.
Very close to
No.
very, very simple.
I claim no.
Oh.
I claim no.
Is that because we can't?
Huh?
We don't have such a number, so
What do you mean?
Sure.
No, you said you can have a number, right? Yeah.
It's never very close to zero. It's
Yeah.
It's close.
Yeah.
So
Uh-huh.
it's the
I think
Mm-hmm.
we can't find such a number, but it exists.
yes. We can not only get zero, but it's close.
I say it doesn't exist.
It's
Because if you pick one, then I can pick -1 over I plus I+1 to get smaller. So I keep going smaller, keep going smaller, keep going smaller.
It doesn't exist such a number.
Yeah, doesn't exist. Yeah, because doesn't exist such interval, close interval, because I can keep going small, keep going small, keep going small. Just +1, +1. Yeah. Okay. I passed the deadline Please now you can sign it. Someone asked me that whether screen is gone. Try again. Okay. So some of you think that this answer should be a closed interval, another closed interval. And my claim is you cannot find such closed interval because if you have such closed interval, I can find a smaller one. I can find even smaller one. So suppose you think that it's like suppose this is the smallest one, but I can find even smaller one. But over k plus 1 over k plus 1 is even smaller. Space. Smallest interval. Okay. So you can keep going small, keep going small. Then the only number that less than all these numbers is 0. Greater or less than. That's why we get 0 in this case, a singleton. So a set containing one element we call a singleton. I didn't introduce this in any place. So a singleton is a set containing get a singleton. Okay. Okay. So let's look at this Venn diagram representation. So over here we got two set A and B potentially intersect, and we have this universal set that contains these two. Okay. So try figure out how to represent the shaded region inside these 6 examples here. So there might be more answer to one question. You can try. Use the operation that we just learned just now. Hey, I think I skipped one slide. Is it? No wonder I stopped. Finish so fast. Wait, before that, I skipped one slide. Let me go back. There's a difference I forgot to introduce. So before you do that, the Venn diagram. So let's see. So I skipped one slide here. So let's see what's the relation between the cardinality and the union and the intersection between sets. So two sets are disjoint if their intersection is the empty set. Okay, so why I talk about this definition here? So there's a theorem which you can prove, or you can look at the book. There's a proof there. So if you take the union of set, okay, and you count them, it's equal to the sum of the individual set minus the intersection. Okay, so if the two sets are disjoint, then this is 0, right? So if you take the union of two sets, it's just adding up the number, the cardinality of them. Okay, but if they have the intersection is non-empty, then you will add out an extra intersection here. So you need to take it away. Okay, this is the idea behind it. So the other one is actually taking the difference. Okay. This one is important. So let A and B be set. Okay. The difference of A and B denoted by A minus B is the set containing those elements that are in A but not in B. Or we will write A slash B. Okay. So what's the difference between this one and the previous one? Previous one is the universal set. So the A here sometimes should not sometimes, but always is the bigger one. But this one, these two might not have any subset relation to each other. For example, okay. For example. So okay, let me write out the set builder notation. Okay, for example, we can take the difference between these two sets. Okay, they are not subset of each other, but we still can do the uh, set difference. So what's the set difference between these two? It's something in A but not in B. Huh? 5. Yes. Okay. So also you can note that if I take this to be A and then take this to be, you can try, okay, try and find B minus A. So they are not the same. So this is not commutative as well. But this one is more intuitive because like 2 minus 3 and 3 minus 2 is different. Okay. So sometimes I think better if we use a difference of A by B, then we know that which one is the prime one, which one is the back. Because the order is important for this difference. Okay. So we learn difference, we learn union, we learn intersection, we learn complement. Okay. So try and work out how you build this shaded region here. There might be more than one way to write it out. What's your try on the first one? Try. What is this shaded region here? Huh? Huh? Conjunction. Oh, conjunction. Okay. Conjunction we usually use for logic. So it's A intercept B. Right? Any one road B intercept A? B intercept A. Yeah. Okay. They are both work. They are the same. Okay. How about 2? A union B. Okay. Any one road B union A? Yeah. Okay. Same. How about 3? Hmm? 3 is what? Complement A complement. A complement. U minus A. U slash A. Any other answer or not? If you have, you shout out. Shout it out. How about 4? A minus B. Okay. Difference of A by B. So other answer or not? Huh? Intercept B complement. A intercept B complement. A intercept 1. Okay, yeah, good. Okay, can. Yeah, sure. I think this is the definition, right? Yeah, this is the definition. Good, very good. Okay. Anything else? About 5? Huh? Who's saying? Yep. Yep. A complement intercept. What? Oh, doing 6. Okay, we'll move it to 6 first. Okay, how about 5? Huh? 5. 5. Understand. Yeah. Okay. Sure. Anything else? Huh? Is anyone saying anything? Say again. Say again. A. A what? A complement intercept. A intercept. Uh-huh. Union. Okay. Like this. You want to check? A intercept with B complement. A intercept with B complement. Okay. And union with B complement. Yeah. Okay. Yeah. Sure. Mm-hmm. Mm-hmm. Yeah. Okay. Mm. Can. 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 Okay. And six, someone says that A complement intersect with B complement. Yeah. Any other answer? U minus A union B. Actually this one is the A union B complement. Okay. So this is like it should remind you as a De Morgan's, right? Pair complement, and then you turn this uh, union to intersection. Okay. Yeah. So any other interesting one? Interesting attempt? No? Okay. Yes, that's right. So we have a similar identities here. So we also got algebras here. So if you remember the propositional algebra, we got all the conjunction, the disjunction and the conjunction. Okay, so similarly we have that in the set theory, the union and the intersection. We also have this identity laws, domination laws. Okay, remember the take conjunction with the true or false statement. And idempotence law. Okay, idempotence law, I think here is pretty straightforward, right? Because if they are the same, you just intersect the same thing or you union the same thing. So you get them back. And then also have this double negation law, but it's called complementation law here because it's taking complement, double complement. And then commutativities law, associativities law, distributivities law, De Morgan's law. Okay. Absorption law, yeah, absorption law I think is more intuitive here. Okay, if you think of it as a set. So if you intersect extra set with A, so potentially you get a smaller set. But if you union with A, you still get back all the A. If you union with another B, but you need to take intersection with A, so you going back to A again. So absorption law, I think, is more intuitive here. And complements law. So this one is, remember the P or not P, P and not P is a contradiction or a tautology. So this one is for the set. So actually, this is not a coincidence. So these are the special realization of general algebra called Boolean algebra. So Boolean algebra is an algebra with two operations, okay, such that they satisfy this kind of law. And we will return to Boolean algebra in the last topic in this course here, Boolean algebra. Okay, so as a tradition, we will prove one identity here so that you know how to do. So in your free time, you can try and prove these identities at home. Okay, so prove this identity. So this is one of the technique you need to master. So to show the equality of set, you need to show two set equalities. No, two set inclusion. Okay, to show two set inclusion. And set okay, so let's try the first one. So let's take an arbitrary x in the left hand side. Okay. So then what do we have? Then x is not in A union B. So this one is by definition of complement. then X is not in A, or so it's not the case that X is in A or in B. Okay, this is the what this is translating to propositional logic. And then from here, since this is a propositional logic, we can use the De Morgan's law here. So this is not in here, and not X is in 2. So this is by the De Morgan's law. So since we have set theory now, so we should say this is the De Morgan's law in the positional logic. Okay, and then since it is not the case that X is in A, this means X is not in A, and X is not in E. Okay, this is by what? This is just translate back to theory. Okay, so which implies what? X is in the complement of A. Okay, since I use bar here, I use bar to be consistent. B bar, this is the by definition of complement. Okay, which implies X is in A bar. That's it. Okay, this one by definition of intersection. Okay, so we get A union B is in the subset. Okay, so I left the other one as an exercise. Okay, do a similar step. And actually, in your textbook, they present another method, which is called the membership method. So this membership method should be reminding you of the truth table. Okay, so how this table works? Let me draw this table first. Okay, similarly, you also fill in the A, B, A bar, A union B, A union B bar, A bar intersect B bar. Okay, and then so the one here, so we use 1 and 0. The one here will indicate a specific element. Okay. So for example, we also have 1 1 1 0 0 1 0 0 here. So let's see what's the 1 1 doing. Okay, let's see we have, let's say we have a 2 set here, A, B. Okay, and then 1 1 will represent the element inside the intersection of A and B. And then 1 0 will be looking at the element inside A. 0 1 will be looking at the element inside B. And then 0 0 will be looking at the element outside A and B. Okay. So this will study all the elements inside the set you need to study. Okay. So if the element is in A, then that means it is not in a complement of A. If it is not in A, then it is in the complement of A. If it is in B, then it is not in the complement of B. And then if it is not in B, then it's in the complement of A. So let's look at A union B. So if the element is in A and in B, is it in A union B? Yes or no? Is it in, if the element is in A and the element is in B, is it in A union B? Yes. Okay. If it is in A but not in B, is it still in A union B? Yes. Similarly, 0, 1, you get 1. 0, 0, you get 0 because it's not in A or not in B. So you get 0, 0, 0, 1 on here. Okay. And then what is A intercept, A bar intercept, B intercept? Okay. So if it's not in A bar, if it is not in B bar, then it is not in the intersection. If one is not in the A bar, then automatically it's not in the intersection. Similarly, for this one, it's not in the intersection. If it is in both complement, then it is in the intersection. So they will have the same membership table. So this one also can. But I would prefer the set inclusion. So you must learn the set inclusion method. Okay. Okay, next. So next we will go into define the multi-set. Okay. So what's a multi-set? So multi-set is also an unordered collection of elements, but we allow the elements to repeat. Okay. And we allow the elements to repeat. For example, we have 1, 1, 1, 2, 2, 2. Okay. This is a multi-set. Is a multi-set. Okay. Next. So we would like to say how many times an element appears inside this multi-set. So we'll call it a multiplicity of the element. So the number of times appearing in the set is the multiplicities of A. Multiplicities of A. Okay. For example, what is the multiplicity of 1? Of 1 in the previous multiset? What's the multiplicity of 1? 3. Yes. Okay. How about 2? Yes. 3? Yes. Correct. Okay. So then we also want to count the cardinality of the set here. So the definition of the cardinality of a multiset is just defined to be the sum with sum of the multiplicity of the element. Multiplicity. Okay. So for example, what is the cardinality of the previous multiset? What's the cardinality of the set? 6. Okay. Why is it 6? Because it is 3 plus 2 plus 1. So you add out these 3 numbers. Okay. 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 So we'll okay. Before going to the union thing, actually you can try to define try define the subset notion for multiset. Okay, it's similar, but the union here is a bit different. So if you want to consider the union of the multiset, you actually need to consider the maximum of the multiplicities that the element appearing in P and Q. And intersection, you need to consider the minimum of the multiplicity of the element appearing in the two set. Okay. And the difference is you take the difference. Okay. If it is negative, take the difference and then take the maximum between the difference and 0. Because sometimes you will get negative, but there's no negative element inside your set. So you take 0. And the sum, this is the extra thing for the multiset. The sum is the sum of the multiplicities of the elements appearing in P and Q. This is the naive union you might take at first. Okay. Okay, let's do some example to see what's going on here. So if I want to take the union, I need to take the maximum of the multiplicity of the element appearing in each set. So for example, the first one, it appears 4 times. Okay. The second one, it appears twice. Okay. How about 2? The first one, it appears how many times? 2. The second one appears 4. Okay. And then for 3, the first one appears once. And then the second appears twice. Okay. So that means in my union, I have 4 ones, 4, 2, and 2, 3. So the set is looking like this. Okay. This is how you take the union of multi-set. How about the intersection? Intersection, we take the minimum of this appearance. Okay, so I get 2 ones and 2 twos and then 1 3. Okay, how about the difference? The difference, we take the maximum of the first appearance minus the second appearance and then choose between this difference and the 0. And then we take the difference and then choose again 0. And then take the difference and then choose again 0. Okay, so the first one is the maximum between 2 and 0. So we pick 2. And then the second one is maximum between -2 and 0. So we pick 0. The third one, we have -1 and 0. So I pick 0. Okay. Okay. The fourth one is the max. What is this? Oh, so this is just the adding up the two sum, the two multiplicity. Okay. So you got like 6, 1, 6, 2, and then 3, 3. Okay. Yeah. So in previous class, they asked me one of them. They asked me, can I replace this 0 with something else? Maybe put a 2 here. So if you put a 2 here, if this answer come out to be 1, then it is false already, right? Because there's only one exists, but you have to pick 2. So 0 is just there to like remove the negative. Yeah. Remove the negative answer. And okay, so you can try to do an exercise. So try find b minus a. Right? And then you'll see that b minus a and a minus b is different. So in a nutshell, what do you have? So a union b, actually you just have the largest thing you have from each set. Okay, a union b. A intercept b, you have the smallest. So you have 1, 1 here, 2, 2 here, 1 here. Okay. A minus b, so you take A and then minus all the things in B. So you take away 2 1s. And then you take away 4 minus 2, 4, 2, but there's only 2 2s here. So you take all of them. Similarly for 3, you have 2 here, so you take all of them here. So you're left with 1 1. A plus B is just like adding up all of them. Okay. Okay. And any question or not? Any question? Any question? No? Mhm. Yep. Hmm. You mean you understand like this? Uh, I think, let me think. Uh, to avoid confusion, usually we will put bracket, but I'm not sure. But for me, I don't think the book mentioned anything about this. But okay, I think they mentioned about the negation thing. So if it is negation, they will take negation first and then like this. This is what is stated in the propositional logic. But to avoid confusion, better you write this or you write this. Otherwise, I think they will read as this. Hmm. Yeah. Always. Any other question or not? Do you want to go into new content or you want to discuss, please? Huh? What? So like the next, I mean, the next week we'll finish the set theory. So we got functions, we got matrix. I think functions spend around a bit more than 1 hour, and then matrix. Then we'll finish set theory. And then we will go into counting. Then we will have quiz again. Quiz again on set theory. Hey, you guys want to have new content or you guys want to have quiz discussion? Hmm? New content. New content. Wow. Later I teach too fast for you. Okay, maybe we talk a bit. Okay, we talk about some ideas in function. Maybe we won't go into all of it, but we will talk about a little bit. Give you a little bit idea on the function. Okay, but we won't go into too much detail yet. Later we're going too fast. So I don't know because in the note they have in the textbook they have sequence, series, and then cardinalities. I don't want to go into those things because they just touch on it. If you just touch on it, then I cannot, how to say, you cannot master so many, how to say, so many little things. It's very hard for me to test you. Like you learn it, but you don't learn it deep. So I don't go into those chapters, the subtopic. For example, the cardinality part. If I teach you the big theorem, like I don't know, but you can read on yourself. So I try not to go into. But I try to like focus on something concrete that I can test you. So. Okay, so function. Okay, since we are too early ahead of time, so what is function to you? fx fx equal to x, fx equal to x squared. What is function to you? When you first learn. How do you think about function? Louder. Oh, domain and range. Okay, I think that one is pretty good. Yeah, domain and range. Okay. So function actually is a mapping or a transformation. So if you hand me an input, I have to give you an output. Okay, this is the function. If you give me two same objects, but I give you different output, then this is not function anymore. It's not well defined. So every input has one output. Okay, this is function. That's all. This is function. Okay. So why this functions is put behind this set here. So function is for you to go between set. So let's draw this thing up. So let's say we got A and B set. Okay. So these are two sets here. So we want to go between them. Okay. How to go between them? So we create a thing called function. Okay, so maybe these are the element here. Maybe like x1, x2, x3, x4, x5, x6, x7, x7. Okay. So the other side you got like y1, y2, y3, y4, y5, y6, for example. So you want to go between this set here. So you need to tell me. So F is actually an assignment. Okay. Assign xi and yj. Okay. So different assignment will give different 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 object. Okay. So for example, so fx equal to x. So this one doesn't make sense if you don't tell me the domain, right? So actually, the domain you care about previously was x is in real. Okay. So this means I have a real line. Okay, real line. I draw it vertical now. Okay, you need to tell me how this number goes. to another real line. So this one is going from, so two set. What are the two set? So the two set are reals. Okay, going from real to real. So this one is kind of a boring one. So you just go to your function. And maybe a bit non-trivial one, fx equals to 2x. So you give me an x, I hand you a 2x. So you give me 1, I give you 2. You give me 0.5, I give you 1. So it's like scaling the graph. So for example, so you hand me 0, I get 0. You hand me 1, I get 2. You hand me 2, I get 4. Okay. So something like this. Okay. So you will sketch the graph, something like that. Okay. So this is function. And just now Godfrey talked about domain and range. Okay. Yeah, domain and range. So in this abstract case, right? So if you assign, you can see that here only have, what is the cardinality of this set here? Set A. What's the cardinality of set A? What's the cardinality of set A? Huh? What's the cardinality of set A? Huh? What's the cardinality of set A? 8. Okay, good. So what's the cardinality of set B? 6. Okay, good. So that means there must be 2 or more elements that get sent to the same thing, right? Because you only have 6. So what's domain? So domain will be in this. So domain is the is where the function have values, and codomains is where the function give you the value. Okay. So why would we have range? Okay. The relation between range and codomain is subset relation. Okay. So because the set, okay, so yeah, so the subset relation, so this is the codomain. This is the relation. Okay, so you might not reach all the point here. Okay, maybe I can do something stupid. So I can say I want to send x1, x2, x3 up to s8 to just y1. To just y1 here. Okay, then this is the range I get. So this is my range. Okay. So the cardinality of my range is what? Is what? Okay. So the set of my range is just y1. So the cardinality of my set is 1. Okay. Which is less than 6. Less than the cardinality of B. Okay. Yeah. Okay, this one just some motivation for the next chapter. And we will make this precise next time. Okay, so we go into break, and then I want to have like row by row to select your quiz so that there's no congestion. And then after you take your quiz, right, you can take a photo, and then after this class, give me back the physical copy. Okay. Start with that row then. That row. 4 rows, and then row by row, come and collect your quiz. And then we'll have a break. 10:56. Please search for your own quiz. You might change your quizzes from last time. I mean, change your position, sitting. Just leave it here. Leave it here after you found your quiz. Leave it here. After you found your quiz, leave it here, and then people can come and get their quiz. Yeah. Physical identification. Okay. You want to help take the photo? What? And then
you go to examination, physical examination, and count. He
okay.
not able to count.
Okay.
Okay.
So what do
He
you want
told
to
me to tell you this. He asked for the
ask him to email me? Ask him to email me.
okay.
Yeah. Yeah. Okay. 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 What? A bit cold. Sweating cold. Fever. Okay. 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 Hey, the quiz pass around already. Okay. Okay. Never mind. Just pass it. Just pass it. Here got some more. Cannot find your quiz? Huh? 好，哦，你可以拿着先哦，如果要拿着先，等下放钱一下。啊？Total marks 10 out of 10 out of 10 out of 10 out of 10啊？Altogether 10. Yeah, because it's 100. So since it's divisible by 10, so I just divide 10 every.
这个问题有答案。
就是比特币成分，然后没有教过那个词。
不太会标。
啊，等一下，我会讨论，我会讨论，我会讨论。如果再不明白，再。这个是想说，这是想说，
第一集
对，就是我要，就是逻辑对。等一下我会讨论那个答案先，然后你听了不明白再。I think so. I mean, just translate to 4%. Yeah, I try to make it 10. Yeah, yeah. If there's change, I also maybe there will be change, but for this one, it's out of 10 marks. Initially, I made it 100 because maybe I got like, how to say, 0.5. So that's why I made it 100. But since after the adjustment or divisible by 10, so I just make it out of 10. Try to make it out of 10. If accidentally make it 12, then maybe that quiz will be 12. But every quiz will worth 4%. Yeah, yeah. Yes. Yes, 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 yes. That's right. That's right. Is everyone getting their quizzes back already? Not yet. Please pass around the quizzes, okay? After you find yours. The attendance is done. This one done. Done. Okay. Okay. Maybe. Few more. Few more. And let the last row. Okay. Maybe I start discussing a little bit. Okay. So the first question here asks about is this a proposition? This is quite similar to your tutorial question. So it's not a proposition because it is a question, or it has no true value, or you cannot determine whether it's true or false. Okay. Somebody write because it is not a statement. So I define statement and proposition to be the same. So it is like repeating the answer, not answering the answer. Next is the most common one should be KFC Roti is better than Starbucks. Okay, as well as the proposition I will accept. And then 1.3, what is it? Actually, what is this question asking? So when is the proposition you make just false? So if P is false, then not P is true. So it is when not P is true. Okay. When P is false, not P is true. So this means this question is asking about the negation of the statement. Okay. The third question is asking about the negation of the statement. Everyone got the quiz back? Got the quiz back? Pass me the remaining one. Pass the remaining one to me after everyone got the quiz back. Okay. And then the next one is I give an example of compound proposition. Okay. So one thing you need to know is to realize that whether the sentence is a proposition or not, and then make out of what proposition, and then how the proposition combine, or make into compound proposition, and then realize that the other compound proposition is the contrapositive of the first one. And then this question asks you to show the logical equivalence between these two, between the statement and its between the conditional statement and its contrapositive. Two ways to show: you can show that either both of them has the same truth table, truth values, or they are all the biconditional statement is the tautology. There are two ways to show it. Okay. So everyone got their back. Okay. So maybe share some interesting answer here. So I compound some interesting answer here. So okay, so this question for the first, okay, you'll see that actually this I put some machine and human here. So actually I have 4 questions at first, but I removed 2 because due to time and also stupid system in the university, then I need to like specify what skill that you need to learn in this quiz for each question. But nonetheless, so in first question, so actually you don't need to understand what is KFC fully or Mama fully or Better fully or Drumstick fully. You don't need to understand all this. You just need to know their objects and adjective is enough to answer this question. Okay. So you don't need to find someone that don't like this or like this. Okay. So because logic is true regardless what people think or regardless anything. So that's why when they build the robot, right? So when they build the robot, they use this proposition, true or false. That's why the robot is has no feeling. Okay. Because they don't feel what is better. They only know better or not better. Okay. So logic is like this. So someone said that it depends. Some people like KFC drumstick, or some like drumstick. I think this one, to be honest, in my homeland where I was born, there's no Indian Muslim there. Okay. Yeah. Okay. This one, yeah, this one maybe just skip through. This one is don't know what happened. Okay. Okay, this one, somebody changed my better to delicious and then cheaper and then yummy and then bigger. In general, don't change the adjective unless they are equivalents. Or maybe it's delicious is better for you. Okay, this one is really good. Okay, this one. Okay, someone from interesting proposition here. So someone said that if only if it is on the weekend, then KFC drumstick is better than Mama. And someone formed P or not P. P or not P is a tautology, so which is never false. For part 3 is never false. And someone formed contradiction, P and not P, so it's always false, no matter what. And the proposition is always false. Okay. And then this one, okay, someone quantify the better. So he wrote the better and then he defined some symbolic notation for it. So it's like in the class, I did some less than 0, right? Less than equal to 0, something like that. So he used that kind of notation. Is it in this class, this guy? I know if this guy is in this class or not. And this one, this is quite good. If you prefer to Indian cuisine, Mama is better than KFC drumstick. So when you prefer to Indian cuisine, but KFC drumstick is better than Mama, then it's false. And then this person here, so he wrote out the negation and then he suggests how to test it. And I think this guy is from this class. Who is this? I want to see you. Who is this? Is he here? This person here. Is it? I think Tan. Tan. Okay. Let me check the name. Tan So Seng. Who is Tan So Seng? Oh, you. Okay. How you come up? How you come? Can I ask you how you like come up with this proposition? Uh, just come out like that. Actually, this is the motivation why I wrote this question here, because the first day I arrived in here, I was booked to the mama restaurant, but I tried the drumstick. I think it's just okay, but it's kind of expensive. Yeah, so that's why I come up with this question. Also, in my homeland, there's less mama. There's no much mama. Huh? Sarawak. Yeah, not many Indian and not many Indian. So yeah. Okay. Okay. Any question on the quiz? Any question on the quiz? Okay, if not, then let's spend till 11:30 do the tutorial question and then we will discuss together. Yep. I can hello. After class you can come back to me. The quiz can stay with you until the end of the class. I don't know about your class, but the other class, some of them use the Chinese text to answer question and study. But you can use Chinese text to help you understand the English question, but make sure you learn how to read the English question because the exam will be totally in English, no Chinese. Do you need more time or you want to discuss now? You want to discuss now or you want more time? More time. 3 more minutes, 2 more minutes. Hello. Hello. Okay, let's start. So 2.1.2. So they give you the roster method to list up all the item. Ask you to use the set reader location to write. First one. Yeah. Okay. Sorry. Let me do it again. Okay. Again. Okay. So you're given the rooster method to list out the set. elements, but you are asked to give the set builder notation. So one way you can do is you notice that it's a multiple of 3, and then it's in between 0 and 12, or you can take n to be 0 to 4. And the next one is you can realize that they are in the integers. And then the fourth one, you can see that they form a word monopoly by 1/n1. Any others have different answer or not? They have different answers. They have different answers. Different way to describe. There's no right or wrong in this question, but if you have, then we can discuss. You have different answers? What's your, did you try? You skip which one? You skip C. Very smart. Skip C. Very interesting. Skip C. Anyone try C or not? Anyone try C? You try C? Huh? Uh-huh. All 13 letters or 17 letters. Okay, yeah. Yeah, you can do that. Unless you got the order on the order on your alphabet. If you got order on your alphabet, then you can do it. Okay. Yeah. If you have order on your alphabet, then you can. Actually, this order is actually like the function mapping. It's the function. So you map between numbers and the alphabet. Okay. If not, then we skip to the next one. So 2.12. Okay. So the key here is actually to understand whether these are the same or not. If you understand this, probably you can try all these questions here. So is empty set equal to the set of empty set or not? Is empty set equal to the set of empty set? So if you want to show them they are equal, you need to show two set inclusion. So the empty set is a subset of the set of empty set, and the set of empty set is a subset of empty set. So the first one is always correct because empty set is a subset of any set. Right? We already proved it. And how about the other one? So to show this, you need to show that for every element here, you need to show that it's an element here. Right? But if you take X to be the empty set, you have to show that the empty set is an element of empty set, which is false. Why? Because empty set has no element. So this one's false. So that means this is not equal. And then yeah, any problem you met when you do 2.1.12? Do you understand the proper subset notation? What's the what do you mean by element? G. Huh? So G, so they repeat the element here. So actually in set they are equal to just one element here because set just care about distinct element. If multi-set, then you have two, but in set you just have one. Okay, but G asks for a proper subset. Okay, So as of for proper subset, this means you need to show that the left-hand side is a subset of right-hand side, and also there exists an element in right-hand side which is not in the left-hand side. Okay. Which the answer is false because you can't find an element in right-hand side which is not in left-hand side. Okay. If this is a subset, then it is true. If it is proper subset, then it's false. So for proper subset, you need to check two conditions. You need to check it is a subset, and also there exists an X on the other side, which is not on the left-hand side. On the right-hand side, there's not an element. Okay. Yeah. Yeah, so this one is true. Okay. Any other question on this part? No? No? Feel free to ask me and then I will come back. So next, see, next. Okay, next. Cardinality. So cardinality of set. So cardinality of empty set is 0. Cardinality of a set containing an empty set is 1 because phi is the element here. Cardinality of set containing empty set and the set of empty set is 2 because phi is in here and then set of empty set is in here, so 2. So the cardinality of the set containing empty set, set of empty set, set of set containing set, empty set, and set of empty set. So it's 3 because you have 1, 2, 3, 3 here, 3 element here. Yeah, so it's 0, 1, 2, 3. So remember last time I introduced the piano axiom 0, 1, 2, 3 here. So this set here correspond to these numbers here. 0, 1, 2, 3. Okay. Yeah. Did I tell you how the natural number come out in the human history? No, never. Oh, okay. So the number is because during the old time there's a shepherd, right? You know shepherd? So they wear the shoes. So they want to compare their shoes. So whose is more than whose, right? So they come up with this. I got one sheep, you got one sheep, I got two sheep, you got two sheep, three sheep, three sheep. So this number become an invariant of the herd of sheep. Okay. So instead of you talk about sheep, you talk about numbers. Okay. 2.1.124. Can you conclude that A equal to B if A and B has the same power set? Yes or no? Why? Why yes? Why? Why? Huh? A equals to B. Why A equals to B? So if you take the union of the power set, right, it's actually just the set itself. Okay. So you retain the set. Yeah. This is what I wrote here. So you take all the set in your power set. Okay. Remember the example I gave just now? And then you take union all of them, then you get all the element back. And also you can prove by contrapositive. So the statement is if A and B are two sets with the same power set, then A equals to B. So you can assume A is not equal to B. So they have different elements. And then you can produce different power set. So proof by contradiction also works. Okay. Next, so decide whether 2.1.26 decide whether the set is the power set of some set or not. So empty set is not because power set contain at least the empty set as and what and itself. Okay, so it cannot be empty. B, so this is the power set of A. C, you can see that there's extra subset that it doesn't include. So no, because this set has 3 elements, and it's a fact that the cardinality of power set is always 2 to the power something, okay, which you can prove by induction. And induction exercise proves that the cardinality of a power set is 2 to the some power. You can prove by induction. D, it is a power set, and then just write out what is this power set of power set. 2.1.50 Russell's paradox. So Russell paradox, this question is asking what? So it is asking whether this set exists or not. So what is this set here? So this set is set of all set such that the set is not element of itself. Okay. Set of all sets such that S is not an element of itself. So they want to prove that this set doesn't exist. So suppose X is in X, then if X is in here, right? So I need to satisfy this condition here, right? So X is not in itself, but you contradict with your assumption. If X is not in X, right? Satisfying this condition here, then X is in X again. But contradict with your contradict with your assumption again. So the moral of the story is you need to specify a domain for your axiom. Okay, cannot just consider everything. Okay. Next, 2.2.4. Okay, 2.2.4 is just checking whether you know the definition or not. Checking union, intersection, indifference. Okay. 2.2.12 is something you need to learn. Showing two sets are equal using the set inclusion. Using the definition of union. Okay, just now someone asked a question about maybe you think that this two notation is quite close. So about this one and this one. Okay. So one is a proposition or proposition logic. So one is in the set theory. So one is the N. One is the intersection. Yes. And then they work on different objects also. So this one work on proposition, okay, between propositions. And then this one is between set, okay. Between set. One is between proposition, one is between set. Don't confuse, don't mess up. Okay. Similarly with the union. Okay. 2.2.16 also showing something is a subset. These proof combine set theory and propositional logic. So it's a good exercise to do. The Okay, E, I have something to say. So E, I'm not sure you can show directly or not, but I think that I can't. So I use the contrapositive. So instead of showing the element here is in here, so I show that if the element is not on the right hand side, then it is not on the left hand side. Contrapositive. Okay. Instead of showing everything in here is in here, I show that everything not in here is not in here. So showing the other way. Contrapositive. Okay. Next. 2.2.54. Okay, this one. Okay, this one is this one is close to what we did in the class. So you take union of this AI here. AI is integers, I think. So integers stop at I. So if you take union of them, you are increasing. Okay. So you take the last AN. If it is intersecting, so it's like you need to take the smallest one. Of course, to be really pedantic, you need to show the set inclusion. Okay, can try show the set inclusion because maybe I will ask in the exam. So try show with set inclusion, prove that they are equal. And then the next one we try with different set AI. So for part A is starting from I and then go on forever integers. So if you take infinite union of these, you will just get AI because AI is the largest one, right? If you take the intersection, so this one is getting smaller towards infinity. Okay, but infinity is not in the set, so this is an empty set. There's nothing in there because everything. If you found someone in, if there is someone in here, you can find an n such that the n is larger than it. So you cannot find anything, any number here. So it's an empty set. How about this second? Second is just a tuple here. Okay, but unordered tuple. So it's like 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. So if you take union of all of them, you get all the number. Okay, natural number. And then if you take intersection, so each of them has 0. So only 0 is in there. Okay, and then this one, open interval 0 up to I. So if take infinity, then you have the open interval from 0 to infinity. Not that this is not closed, this is open. So you can never attain infinity. And if you take intersection, so this AI is growing bigger, 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 and bigger. So intersection is just taking the smallest one. How about this one? This one is going the other end. So getting smaller, 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 smaller. Okay. So if you take the union, you will get the largest guy. If you take the intersection, you get the smallest, which is empty because you can't reach infinity. This one also cannot. This is an open interval, so doesn't have infinity. Think normal. Normal. Okay. Any question or not? You want to run through again? Huh? What? Any question you want to run through? Run? Huh? Huh? Need some time to think. Which part? Oh, oh, okay, okay, okay. Okay, meet me next Tuesday. Okay. Yeah, meet me next Tuesday. Okay. Hey, I don't know whether this content is too easy or for you or you need to learn more about it. Sometimes you don't have sound, I don't know whether it's easy or huh? Some part is difficult. Okay. For example, where? Let me know. This one. This one. But my explanation making sense of it. Huh? Doesn't make sense, eh? Doesn't make sense, ah? Hey, don't. uh, makes- okay, make sure. Okay, just ask me if I'm talking to myself. Okay, if no question, then we can dismiss. Hey.
Say
Different.
different. This one.
This one, and this one is the same.
This one is the same.
Yeah, this one. Is the same. Okay, thank you. Okay, give me back your paper, please.
This one. Okay.
This one. Is the same. Okay.
Thank you.
Thank you. Thank you.